Okay, so let's talk about RL systems. You have gotten away with only having to focus on RC systems. We're going to talk about RL systems. Now, RL systems are just like RC systems. Okay, good talk. All right, we're going to start with our voltage source here. We're just going to plug it in series, resistance, and inductance. Okay, we'll say Vs is equal to 24 volts. We'll say R is equal to 1,000 ohms. And we'll say L is equal to 2 henries. Okay? Now, the question that I'm going to ask you is, what is the function that defines the current through the inductor? How do we solve this? What? Did you say shame?
Check.
Chegg. Thank you, Chegg, and all of your almighty knowledge. If any of you go on to take the FE exam, you'll have to make sure to bring up Chegg when you go into the Solution Center and be like, hey, I'm here to take the exam. I want to use Chegg. Can you accommodate for that? And they'll be like, oh yeah, sure. Give her handy dandy Chegg solutions guide. In fact, we'll just hand you the answer to these problems. What? Pretty sure. They're very I mean, they're used to engineers going out and just getting the answers handed to them. Well, the solution method is the same as we did for RC systems, step for step, okay? And I didn't exactly give you those steps correctly the first time, so I'm going to give them to you again. First step, draw your circuit. Second step, derive your constitutive equation. Oh, dang, no. This one is get your equation sets. Step 3, this is when you derive your constitutive equation. Step 4, solve for S, which involves using the homogeneous equation, which means you remove the forcing function. Step 5, solve for a particular solution, which involves using the non-homogeneous equation. And then step 6, I feel like I'm missing one again. What? There is a step that goes right here. There's one right here. This is step 5. Thank you, Gabby. Okay. Step 4 is assume a solution. I should really bring my notes. Step 5 is solve for S, homogeneous. Step 6, solve for particular, which is non-homogeneous. And then step 7, which is solve initial conditions, which will give you your transient solution, scalar A1. Okay, there, now I have all 7. So this is the steps we used last time. This is the steps you use to solve every RC, RL, RLC circuit. LC circuits too. We use these same 7 steps. Now, when we get into RLC circuits, this actually becomes different. This changes. We'll talk about that next week. We'll introduce it next week. Like I said, though, there's not going to be RLC stuff on the exam. There's only going to be RC and RL stuff. But we'll get there when we get there. All right, so I've done step 1. What is step 2? We need our equation sets. What are the 3 equation sets? Let's start with KVL. Okay, how many loops do we have? We have 1. So what is our KVL equation? Yes. The voltage across the battery, which is the input voltage, is equal to the voltage across the resistor plus the voltage across the inductor. All of that forms one loop. So that's equation set 1. What is equation set 2? Somebody other than Dylan. Somebody other than Jacob. It's KCL. I knew you were going to answer too. I just was hoping to stop you before Dylan. Dang it. Okay, how many nodes do we have in this one? How many nodes could I put up there? I didn't draw them up. It's, you know, the worst part about me as an instructor is, like, it's more annoying when students are right, you know? It's just frustrating because I'm like, I don't know. I'm kind of a jerk that way. Yes, Jacob, you are correct. And you should be proud of that, as much as I'm giving you a hard time. So we can get 3 total KCL equations. And I certainly am not trying to discourage you from speaking up in class. I'm just picking on you because you're right. Dang it. I mean, she knows me well. Okay. What are our KCL equations? We have 3 of them. IS is equal to IR. Okay, that's one of them. IR equals IL. Okay, that's at node 2. It's coming in, going out. What's the third one? IL equals IS. Okay, it's coming into node 3, going out of node 3. All right, so this is equation set 1. This is equation set 2. What is equation set number 3? What is it, Jonathan? Component equations. Okay. Now, we have 2 components here. If you get one of them right, I'll give you the other one. What is one of our component equations? V equals IR. Good, pick the easy one. Way to go, Tall Gaiden. VR is equal to IR times R. The voltage across the resistor is equal to the current through the resistor times the resistance. That's our one component equation. I said I was going to give you the other one because we haven't really dealt with it a lot. This one is VL is equal to L DIL dt. The voltage across the inductor is equal to the inductance L times the derivative of the current through the inductor. Okay? Because we have an inductor, this is why this equation is here. You'll notice this isn't the capacitance equation. This is specific to inductors. So it is not IC equals C dVc dt, because we don't have a C. We don't have capacitance. This is the inductance-specific relationship for an inductor as the relationship between the voltage and the current in the inductor. Okay? And as tall Caden got, you have the relationship between voltage and current in a resistor. So these are our three equation sets. So we're done with step 2. What's step 3? What do you think, Thick Caden? Derive the constitutive equation. I want to hear you say the word constitutive. Wasn't nearly as much fun as I was expecting. What's with you guys and having right answers? You started this problem. All right, so to derive our constitutive equation, we have to start somewhere. What equation should we start with? Problem is there's a lot of ugly ones up there. Oh, you want to start with this one? I mean, you could. It doesn't hurt anything to start there. I mean, you know what? You said this one. We could start with this one. The thing about this one is it does have IL in it, and that is what we're looking for. I just usually don't have people start with that one. It's kind of a new thing. There's a lot of ugliness up here. I'm going to pick this one here. And I have my reasons for it. You can get the right answer doing it your way, Dylan. That's actually fine. If you start that way, you will get the right answer. In fact, with most of these, if you start them, you'll get the right answer. The issue with taking on an equation that has an IS in it is that we don't know what IS is. IS is a function. So you're not going to want to have IS in your equation. IR, we don't know what IR is. Just like we don't know what VL is. So really you can start with either of those two. I mean, you could even start with this one if you really wanted to. You get the right answer. But it's a little weirder that way. Yep. All right. So, you know what? I'm going to start with your equation, Dylan. Let's do that. VL equals L DIL dt. Just pick this one. It's got IL in it. Okay? So we're just picking an equation to start with. You're going to mess with all of the equations to get the final answer anyways. So, you know what? Why do the same when you can do something different? So, of this is in the format that we want. This one is not. We don't know what VL is. It's a function. We don't know what that function is. We want to get it equal to a forcing function. Okay? What is our forcing function for this system? What ultimately is powering this system? It's Vs. So we know our final constitutive equation is going to have some function of Vs in it. So that's good. So we need to somehow get Vs in here, lose the VL, and gain another IL somewhere with magic. So let's do that. What other equations do we have that has VL in it? That's the only other equation we have that has VL in it. So yeah, we're going to take this and we're going to plug in KVL equation number 1. Vs minus VR is equal to L DIL dt. Okay? Now we have gotten Vs in here now. So that's nice, right? But now we have a VR. What equations do we have that use VR? We only have 2 equations and we just used one of them. So we should probably use the other one, right? What are you thinking, Tall Caden? What's our next equation?
VR equals IR times R.
So we'll just replace VR with IR R. Okay? Now what equations do we have that use IR?
Kcl.
We go back to our KCL, we have 2 equations that we can use. IR equals IS and IR equals IL. If we use IR equals IS, it doesn't really give us anything because IS doesn't do much for us. But if we use IR equals IL, then we get IL times R equals L DIL dt. Now, since we're solving for IL, this is what we want. Now we have our forcing function and then 2 functions of IL. We're going to clean this up, put everything that is an IL on one side and everything that's a forcing function on the other side, just to get it into a nice clean form. And what we end up with is R times IL plus L DIL dt is equal to Vs. And this, because it only has IL in it and the forcing function on the other side, that is our constitutive equation. What's our next step? We assume a solution, okay? What are we assuming a solution for? What is it going to look like? What does that mean? What do I write next? What are we assuming a solution for? We already know what Vs is. IL, which is a function of time, yes. Okay, so we're coming up with, we're assuming what the form of ILT is going to be. What is that form? It has 2 parts, complementary and particular. So this is equal to ILC plus ILP. The complementary part is the transient. The particular part is the steady state. Okay, steady state is driven by the forcing function. Transient is the difference between where the system is and where the system will be when it's in steady state. That's what a transient is. Also a homeless person. Okay, so what is our guess for the complementary solution? What does ILC equal to?
K1 plus K2 e to the...
It is what the book says, yes. I do teach it a little differently than the book. I use A's and not K's, but you can use K's if you want. It changes nothing. For your complementary solution, this is, I'm not going to use a K, dang it, A1 e to the st. And for the particular solution, it's A2. We're just going to use the same thing that we did for VC. It's going to have the same form. Why? Because it's a first order system. The math we're doing is identical. The equations we're going to get are nearly identical. Spoiler alert. Okay, are we done with the assumed solution portion of this, or do we have anything else we need to do? We're done? Like with the whole problem? Oh, we have scissors. Okay, we're done with the assumed solution part. What's the next step? We're going to solve for S. How do we do that? First of all, what is S?
Time constant.
It's the time constant. What does our time constant tell us? It tells us the constant of time. Yeah. It tells us how long this is going to take for the solution to reach steady state. Okay? Yeah, we'll talk about that in a little bit though. Because that's an important piece of this. Let's solve for S. So here, to solve for S, we have to use the homogeneous equation. What does homogeneous mean? You set the forcing function equal to 0. That is important because that's the condition when we're solving for S using the homogeneous equation. What we're specifically solving for is we're looking for a solution where a function added to its derivative equals 0. Remember when I introduced this to you last class? It's all about you have the two conditions. One of them is you have something that has the same time form as the forcing function, Vs, which is a constant. And the other one is you have something that has the ability to add to its own derivative to equal 0. Okay? When we do the homogeneous equation, that's what we're doing. That's what this function is. The whole reason why we have a complementary solution is because this, added to its own derivative, can be equal to 0. Okay? And that's what we're doing. When we set the forcing function equal to 0, we're solving for a function that added to its derivative cancels itself out. Okay? So, I'm going to write the constitutive equation again. RIL plus L DIL dt equals Vs 0. Set this equal to 0. Forcing function is now 0. Okay, because Vs is a constant, we're not expecting that our complementary solution is going to have the same time form as the forcing function. And it doesn't. Our forcing function is a constant. Rick, I am so sorry for you. You are, like, just, this sucks. It is not okay. Stop being so understanding. Dang it. Thank you. I'm just gonna see if I can put this down. I'll just walk away slowly. Now you can at least see a little bit better. However, now you have the problem of I'm going to call on you more often, so. Okay, so this is the homogeneous equation. All this is this thing written where it's missing VS. That's it. That's the difference. Okay, we're going to take this homogeneous equation, and what do we do with the homogeneous equation? We substitute in, instead of IL, substitute in ILC, because we're specifically solving for the complementary solution. Okay, so this becomes R IL comma C plus L DIL comma C dt is equal to 0. Not a big step between those two. It's just we're not looking at this solution overall. We're looking at only this one. Now you'll find, you'll notice, well, no, never mind. I'll ignore that. This is what we're looking for. Complementary solution only. Okay? So now their next step is what? Do we know what IL comma C is? What is it? It's this. So we'll go ahead and plug this in. So R, dang it, times A1 e to the st plus L times the derivative of A1 e to the st is equal to 0. Or you can use your K1, thick Hayden. What's the derivative of A1 e to the st? I've already asked you this question once today. You just bring the s out front. Boy, you get really good at taking the derivative of an exponential function in this class. LS A1 e to the st equals 0. Now, what can we do with this? Huh? We can simplify, just like in everything. How do we simplify? This is present in both sides. We can divide both sides by A1 e to the st. And what we're left with is R plus LS is equal to 0. When we're solving for S, which, by the way, is the title of this step, what we get is S is equal to negative R over L. Okay, what is tau? What's the equation for tau? It's negative 1 over S. So that's equal to negative 1 divided by R over L. Negative R over L. So our tau is going to be equal to L over R. That's just the inverse of it. Tau has units of time here. S has units of 1 over time. Okay, if we're going to solve for what tau is equal to, what is L? 2. What is R? 1,000. So this is equal to 0.002 seconds. Yay. All right, that was fun. What's our next step? What's that? We solve for the particular solution. How do we do that? we use our ILP. Okay, what you do is you go back in here. You don't want here specifically looking for non-homogeneous, which basically just means original. It's original crispy from KFC. We just bring that equation back. We don't set the forcing function equal to 0, but instead of introducing L comma C, we're going L comma P. Okay, so write this again. R IL plus L DIL dt is equal to Vs. Not 0, Vs here because this is non-homogeneous. We replace IL with what? ILP. So this becomes R IL comma P plus L DIL comma P dt equals Vs. What is our next step? We substitute A2 in for ILP because we know what ILP is. It's right there. So this becomes R times A2 plus L times the derivative of A2 is equal to Vs. What's the derivative of A2? It's 0. Second time I've asked that question today. Okay, so what we end up with is RA2 is equal to Vs, which means A2 is equal to Vs divided by R. Now, what is the particular solution again? What does it represent? It represents steady state. So, first of all, what are the units of Vs over R?
Volts per ohm.
It's a volt per ohm. Where else have we seen a voltage divided by a resistance? It's current, and it's specifically current through what? What equation did you use to figure that out? It's Ohm's law, which is the current through a resistor. What you're looking at here is its steady state. The current that's going through the inductor is going to be equal to all of the voltage divided by the resistance. That's fascinating. All right, let's calculate what A2 is. So A2 is equal to Vs. What is Vs? 24. What is R? Okay, so this is equal to 0.024 amps. You'll notice that A2 has the same unit as IL. It should. A1 should also have the same unit as IL. Okay, what's our next step?
Initial conditions.
We solve for the initial conditions. So I'm going to have to erase some stuff again. Another reason why I hate live streaming. Can't use all of the boards like the good Lord intended me to. He gave me these boards for a reason. Okay, now I didn't give you an initial condition when I started this problem, but we're going to go ahead and we're going to assume that at t equals 0, our voltage is non-zero, because why not? It's easy when it's equal to 0. At t equals 0, IL is equal to, maybe maybe at the very beginning, when this power supply is plugged in, maybe there is a negative 0.001 amp current traveling through the inductor. It's small current, but it's going the wrong way. Okay? We're just going to assume that, because why not? We can do whatever we want. It's math. It's a lot easier when it's 0, but whatever. Okay, now what do we do? What do we write next? For both solving for S and for solving for the particular solution, we had to go back to our constitutive equation, and we solved it in the homogeneous and non-homogeneous forms. We don't have another form of the constitutive equation we can solve. So when it comes to initial conditions, we have to solve it using a different formula. Which formula am I going to write right here? It's not the constitutive equation. I just said it's not this one. What is it? Yes?
Where did you guys do this IL from?
Where?
Negative 0.0.
Oh, this? I gave it to you. Yep, that is something that should have been given to you at the very beginning of the problem. I just gave it to you now because I forgot, so my bad. What equation can I use right here? Well, when I'm solving for initial conditions, what I need to know is I have a function, but I need to be able to place it in a frame where I understand what time it is. Okay? So what I'm doing really when I solve for initial conditions is I'm going back to this. I'm taking my assumed solution. I know everything except for A1. So all I'm doing with initial conditions is I'm plugging back in my assumed solution and I'm solving for the one thing I don't know, which is the last piece of it that defines the final solution. Okay, so ILT is equal to ILC plus ILP. What is ILC? A1e to the ST. Okay, what is ILP? It's A2. Okay? Now, at t equals 0, we know IL is equal to negative 0.01 amps, which means at t equals 0, we know this value. We do not know that one. We know S, we know T, and we know A2. Okay, we could also solve this for E is not equal to, or T is not equal to 0. We could solve it where we know that at T equals 1 second, there are this many amps of current flowing through it. We could solve that way if we really wanted to.
Is it 0.00?
Yes, thank you. Keeping me honest here. Yep, that would have been a mistake. Okay, so now we just plug in everything we know into our solution equation. What the initial condition allows us to do is it identifies a point on this graph that we know our IL solution is going to be. Or something. It doesn't look like this necessarily. Actually ends up looking like, it ends up looking like this because it starts negative. T equals 0, we know it's negative, and then it goes up like this, and it approaches the steady state solution, right? So that we know that that's what it's going to look like. All that giving the initial condition does is it says, I know what that point right there is. That's it. Because there's an infinite number of lines that could be approaching that steady state. I mean, I could have this one here, I could have this one here, I could have this one here. When I give an initial condition, I'm saying I pick this line. This line is the one that we're looking for, not any of those other lines. It gives us a singular condition by which we can identify what line it is defining the current. And that's what the initial conditions do. So, I just plug everything in. We know IL at 0 is equal to negative 0.001. We do not know A1. We know S is equal to negative 1 divided by 0.024. We know that T is equal to 0. And we know what is A2? Well, I wrote the wrong answer. This is supposed to be 0.002.024. What is e to the 0? It's 1. So this becomes negative 0.001 is equal to A1 plus 0.024. What is A1 equal to? What's the units on A1? Huh? Thank you for answering. I didn't want to do the splits. It's amps. A1 has the same unit as the current does. Has the same units as A2. Okay? So this is where we stand right here. We have our final solution. IL of T is equal to negative 0.025 times E to the negative T divided by 0.002 plus 0.024 amps. That's the final solution. Okay, now let's ask some questions. What does A1 mean here? Why is it negative 0.025? Why? Why is it that way? Why isn't it 0? Why isn't it 1? What does this value mean? What does this actually mean? Now, hold on. To answer that question, what is this? What is this right here?
Part of the parameter changes with time.
It's the transient portion, right? It's the one that is time dependent. What a transient is it's the difference. It is the way that the system behaves when conditions change. Okay? At t equals 0 seconds, there is a negative current flowing through this, and all of a sudden maybe our voltage source changes. And now it changes to something else. All this is doing is this says, how does the system change from where it's at to where it's going to be? Okay? What does S mean? What is S? It's a time constant. Okay? And specifically, S is what helps us find what tau is, which tau is the time constant. If you look at tau, one thing that I mentioned to you is if we go ahead and plot this equation out, okay, tau is equal to 0.002 seconds, I'm going to go ahead and just plot this like this. At approximately, well, this is at t equals 0. This will be at t equals 0.02002 seconds. This will be at 0.004, 0.006, 0.008, and lastly, 0.01. Now, what is the significance of 0.002 seconds? Where do I have the 0.002 seconds written on the board? That's what tau is. So this is equal to 1 tau, this is 2 tau, this is 3 tau, this is 4 tau, and this is 5 tau. Okay? What happens when you plug in 5 tau in e to the negative t over tau? So at t equals 5 tau, e to the negative t over tau is equal to e to the negative 5 tau over tau, which is equal to e to the negative 5. What is the value of e to the negative 5? Calculator. Anybody know this off the top of their head? The one time I need you, Jacob. I am so sorry. I'm such a jerk. The value of e to the negative 5 is 0.006738, which quite frankly is less than 1%. Okay? What that means is that at 5 tau, when t is equal to 5 tau, whatever tau is, your function, the transient, is only contributing 1%, less than 1% really, 0.6% change to what the solution actually is. At 5 tau, it is almost steady state. Enough so that, unfortunately, this function never actually reaches steady state. But at 5 tau, we actually consider this to be steady state. So here, since tau is equal to 0.002 seconds, this will reach steady state in about 0.01 seconds. That is really fast. Let's plug this system in, bang, it's there. If we increase Vs, is it going to take longer for the system to reach steady state? Think about it. I mean, it makes sense that it should, but if you go back and look at the equation for S, where is Vs in here? It's not. If we change Vs, it has no impact on tau. It does not change how long this takes to reach steady state. However, if we increase the resistance, it will take longer. Why? Because increasing the resistance decreases the current. If we decrease the current, it's going to take longer for this to reach steady state current values. It's going to decrease the DIL dt. Okay? So increasing resistance will make this take a shorter amount of time. My bad. Exactly opposite. It's true for capacitance. Here, if you decrease the resistance, it actually reaches steady state faster because tau becomes smaller. If you increase the inductance, is that going to make it take longer or shorter for this to reach steady state? actually should take longer. Yep, because tau and L are directly proportional. If you increase L, you increase tau. Okay, so like if we would have placed 4 in here instead, we would have ended up with 0.004 seconds. So for an RL system, increasing resistance decreases the amount of time it takes to reach steady state. Increasing inductance increases the amount of time it takes to reach steady state. You also end up storing more energy. So that is the significance of S. The whole reason why we have S is because when we go to plot this, this represents e to the negative 5, which is 0.006 times whatever A1 is. Okay? E to the negative 1. This represents 0.3679, and then it just decreases from here. So this is 0.3679 times A1 plus A2. Okay, and we can keep building out that graph that way. But looking at it in terms of tau, from 0 tau to 5 tau is going to show us a progression of where we start to where we reach steady state. I don't care about the solution past 5 tau, because what ends up happening is, because this is an analog system, there are going to be changes in Vs. Vs may vary by 0.02 volts, sometimes even more. At this point right here, this is within 0.02 volts. So Vs may actually drop or increase. At this point, you're now in the noise level of the actual power supply. Which is why we say 5 tau is close enough. Okay? Power supplies are inherently very noisy. You buy a really, really expensive power supply, they can get a very, very clean one where the noise levels are sometimes on the microvolt level. Bless you. You're talking about a power supply like this, your noise levels are going to be on the point something volts. The stuff that you have for your phone charger, your phone may actually be charging at anywhere from 4.8 volts to 5.2 volts. It jumps that much. There's no control because all of that is being controlled by an outlet where, quite frankly, the outlet is being controlled by a transformer. A transformer is out there in the weather, but that's being controlled by a power station. Power station, as much as it would love to be able to provide consistent power, it's a very noisy process. It's somewhere there's a steam turbine spinning or a hydroelectric turbine spinning, or you have power that's being directly supplied by a solar panel, which then goes into a battery, which acts as a capacitor, which acts as a buffer, whereby they actually have to bleed some of that off, because if you have too much power going into the system, it'll increase the voltage, causing issues. There are a million reasons why power is not constant. So at 5 tau, we assume it's at steady state. Okay? Now the significance of A1. A1 is the difference between where you start and where you end. Here you start at negative 0.001, you end at 0.024. That's it. So A1 is the difference between those two. That's it. This value, the farther you are away from steady state, the larger this graph grows. And that's all A1 represents. It's how far away you start from steady state. Okay, so S is how long it takes to reach steady state. A1 is how far away you start from steady state. And A2 is what steady state is. That's what each of those values means. I like trying to give some significance to why we derive these things, rather than just, here's math, yum yum. Okay, we're gonna take a 10-minute break, come back here at 10:18, and I will see you then. Obviously, I don't